in chapter 23, we talked about one sample t-intervals and t-tests because we had one sample of data and we were looking at the average something or another, right? In chapter 24, we had two sample t-intervals and t-tests because we had two independent samples and we were comparing the two of them. So we were seeing if they were any different from each other. So we were looking to see if the average was any different from 0 for the two groups, right? We had two independent groups. In chapter 24, I talked about a question that didn't meet those conditions. I said that's why there's a chapter 25. All right. So in that example, there was some faculty workout program or exercise program that was supposed to improve your productivity or something. So, or your mood about being at work, something along those lines. So they took 10 people and had them rate their work experience or something before. Then they had the same 10 people rate their work experience after this program had been implemented. So you didn't have two independent samples. Yes, you had two samples, but they weren't independent of each other because it was the same people, right? So in chapter 25, we're talking about all these scenarios where we're not necessarily meeting the independence assumption, okay? So maybe you have two separate samples from two different days, but it's the same people. That's not independent, right? Maybe you have one sample, all right, and you have one set of data, one sample, one set of data, but it involves pairs of people or something. Okay, maybe they did some study with twins and they wanted to see how something was affected or something else. So you have pairs of data. So in chapter 25, all we're talking about is what's going to happen if we do have paired data of some type. Okay, so somehow, some way, you have pairs of information. You have to have pairs for this to work. All right. So in the book, we are talking about speed skating because that's how we got to do things. Yes, they're all foreign, so I'm not going to try to say any of their names. But you have speed skating. So if you're like super into the Olympics like I am, because I'm like an Olympic junkie whenever it's on. Yes, because I just want to sit and watch all of the events. So speed skating, we're talking about like long course speed skating. You have two individuals on one track racing at the same time. Yes, time ends up being what's based on who wins and stuff. But we have two individuals. One starts in the inner lane, one starts in the outer lane, and after so many laps or whatever, they switch so that it's equal but fair about who's on the inner and outer lane, yada yada. Okay? So, looking at this, we have pairs of data for almost all of these sets except for the first one. In the first one, there was an uneven number of competitors, so she's not paired with anybody. And so because of that, we're still going to ignore her because there's no pairs. We have to have paired data. Otherwise, this set of people is a pair because they raced at the same exact time under the same exact conditions, right? Just one started the inner lane and one started the outer lane. All right, so they're not independent. There's not two groups, the inner lane and outer lane aren't independent of each other because two of them are racing at the same time. Does that make sense? Right, so it doesn't meet that independence assumption. Okay? And since they're going to switch lanes in the middle, that lane is independent of each other, right? So you have pairs of data. We have tons of pairs of data. There's more than this. This is just like the top, whatever. This is, from the event. So we have pairs of data. So when you have pairs of data, you have to think about your conditions. And the biggest part, again, is the independence assumption not being met. That's going to be the hardest part of this chapter and of the homework and things like that, is that the mechanics and all that stuff, that's not a big deal. It's not really different from what we've done before. And on the AP exam, though, you'll be given a problem, and it's going to ask you about the average something, something or other. Well, it's easy to know if it's one sample or not. If it's one sample, you had one sample of people. Okay, whoop-de-doo. If you have two sample or paired data, though, that gets a little more tricky because you really have to think about the conditions in the scenario. Do you have two individual samples that are independent of each other, or do you have two samples that were paired by some reason or other? All right, so you really have to think about it. So on some of the homework over the next 2 days, it might ask you to do the correct hypothesis test. So some of the homework, you might have to do a 2-sample t-test, or maybe you have to do a paired t-test. And the reason being is that you need to start thinking through those things. Right? On the AP exam, you're going to have to know which one to do on every single one, and you have to involve all of these tests we've talked about. Right? But here's like the first really conflict of, like the rest of them I feel like you can rationalize out. One proportion, we're talking about proportions, and there's one sample. 2 proportions, there's proportions, and there's 2 samples. Right? One mean, you have 1 sample. But this is the first time there's really a conflict where you really have to think about it. Okay? Is that condition met or not? Okay? Some vocabulary. If you have pairs, we're talking about, we can just call it paired data, but you'll see other terms. When we did experiments, we had blocking. All right? Let me remind you that when you blocked something, it's because you picked a particular characteristic and you ran the entire experiment in both of those blocks. So maybe I thought that some drug affected men and women differently. So I had a drug and a placebo. Well, then I would have the drug and the placebo just for men, and the drug and placebo just for women. Okay? So we blocked that. Well, I can go back and I can compare men taking the placebo to women taking the placebo. All right? And I can put those together because they were under the same conditions, just they were separated. Okay? If you have an observational study, you might see it used as matching. Same thing. They were observing how twins developed over time or something in some characteristic or another. Okay? Well, they were matched together then. So if you see it called matched pairs, or talking about blocking, normally you have pairs of data somehow. Now here is the biggest part of how we're going to do this. I think we all understand that we have 2 people. We're talking about the speed skaters. We have 2 people, but we have 2 times. We have don't have independent. In order to do these tests and these intervals, we're essentially going to do a 1-sample t interval and a 1-sample t-test. And what we're going to do is we're going to look at the differences in all of the pairs. All right? We're always going to look at the differences. I'm going to see the difference in time for the 2 people that raced against each other. All right? And I'm coming up with a brand new set of data that is just the differences. And I'm going to look to see how those differences, if I'm doing a hypothesis test, how different they are from 0. If I'm doing an interval, I'm looking to see the average difference already. All right, so I'm going to be looking at the differences. So in a 2-sample t-interval or test, you are subtracting the average for one group from the average of the other. In this case, you're subtracting every single pair, and you're getting a list of differences. Does that make sense? So with the speed skaters, I'm going to come up with a 3rd list of data. To be the differences. And I'm going to go through and I'm going to do the outer lane minus the inner lane maybe. All right? And I'm going to have a whole entire list of difference in time. Okay? When I have that list, I can find the average of those differences. I can find the standard deviation of those differences. And I can use 1-sample mechanics to pretty much do the intervals in the test. You will not have to do any of that by hand. You're going to do it in the calculator. Okay? But so we're coming up with a 3rd list in this scenario, in all these scenarios. We're going to have a list of differences. Everyone follow me. Clay does, but everyone else follow me. All right. So if you're talking about, we're just doing confidence intervals today. So the first step is your conditions. Your conditions are generally the same. You can still talk about independence, but when you're talking about independence, you're talking about that the differences are independent of each other. So if we're talking about the speed skaters, is each heat independent of the next? Should be. If we're talking about like an Olympic race where, like, they take particular, care of quality of the ice and things like that, then yes. We should have independent races. Now, again, the people within each race are not independent, but the races are independent. The heats themselves are. Okay? So you still need to have independence between the pairs. You still have randomization. You still have 10%. Again, if it doesn't make sense, you don't have to talk about it, but the 10% helps you normally qualify what the population is you're talking about. All right? What is that difference really representing? All right, so that's what helps you out with figuring out. Then you also have nearly normal condition. You need to look at a plot of the differences. So just look at, you're not comparing two plots. Again, we're not looking at outer lane versus inner lane. I'm looking at a plot of the differences. So all those conditions are still there. And then you have to make sure you mention somehow why the data is paired. You can't just say it's paired because you feel like it. Okay? You need to justify why it's paired. So in this case with the speed skaters, I have paired data because I have two skaters competing in the same heat at the same time, and they're going to interchange lanes. Right? So they're not independent of each other. Especially in a race, if Zan is racing against Bailey in the speed skating heat, if Zan starts taking the lead, isn't Bailey going to try to catch up? So those are not independent times. Like it wasn't like it was a blind race or anything. Like they were not going to be independent of each other. Okay? There's like they have to switch at a certain point. It happens in the Olympics. I don't know how that all works. I did not speed skate, but they have to change lanes because of the outer being longer. I don't know. There must be some protocol for that. I don't know how that works though. I don't know. I do, but again, I do not know all the protocols involved. Most times someone's ahead of someone else.
That's true.
Right. But so I don't know what happens if they're at a tie when there's a change. I don't know.
What if they die? Like
Yeah, and then the ice is all muddy.
I know those blades are sharp. I don't know. Okay, that's great. I don't know. We'll look into it, okay?
He was reading about it.
Obviously. All right, so questions about the conditions, though. Yeah, you need to justify why it's paired. All right, so once you've done all that, then you have to name the interval. So in this chapter, we have paired t intervals. So we're still talking about averages, so we're still using t. So paired t intervals, we have paired t tests. In your calculator, because you guys know all this stuff exists in your calculator, there is no such thing as a paired t interval or a paired t test in your calculator. Because the mechanics of both the interval and the test are pretty much identical to a one sample t interval or t test. So because the mechanics are the same, you're going to be using one sample t intervals and t tests in your calculator if you're going to check anything. Okay? All right. So let's look at the mechanics. I can clear all this. If we're doing a paired t interval, we're looking for the mean of the paired differences. That's what this is. It's the average of the differences. So it's the average of that entire list of differences you're going to come up with. Then you have your critical value with n minus 1 degrees of freedom. It is very, very important that you understand that n is the number of pairs, not the number of people. So in the job satisfaction survey we talked about, there was only 10 people. Okay, so it's going to be 10 minus 1, no big deal. And this speed skating example we're talking about, there are lots of different people, but there's not a lot of different pairs. All right, so it's always the number of pairs minus 1. And then you have times the standard error of those differences. So you find the standard deviation or the standard error of the differences by doing the standard deviation of the differences over the square root of n, again, where n is the number of pairs. It follows that same pattern that they've been following this entire time. Statistic plus or minus critical value times standard deviation of the statistic. Any questions? Because the next one we're going to do is an actual interval. The last step would be the conclusion. In this case, you're looking for you're trying to trap the average difference in whatever you're talking about, right? Not just an average in general, but an average difference, because we've actually taken the differences of all the lists. We'll work through that in the example. All right, so here's our example. The table below well, I'll put it to the right, gives the average high temperatures in January and July for several European cities. Write a 90% confidence interval for the mean temperature difference, so it tells you temperature difference, between summer and winter in Europe. Be sure to check conditions for inference and clearly explain what your interval means. We're going to start with the conditions, and I'm not going to write them all down. We are past that in this class. I can talk about them, and you should know what we're talking about. So, independence. In this case, what should I say about independence? Which would mean what? Zane said the pairs are independent, but what do the pairs represent? The cities. So the cities should be assumed to be independent of each other. Okay? You go with that? Were the cities randomly selected? We will assume it's a good representation of European cities. That's what we're worried about. We're looking for the mean temperature difference between summer and winter in Europe. So we have a good representation of European cities. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 cities. Is 12 less than 10% of all European cities? Yes. Oh, good grief. All right. How do we justify that we have paired data? Why is this paired data and not two individual samples of data? It's the same city, right? It can't be assumed the two samples aren't independent because they were taken different times, so we have two different samples, right? But they can't be assumed to be independent of each other because they were taken in the same city. So we have paired data since we have two temperatures per city. The last condition is the nearly normal condition. I cannot do that unless I do some math first. I cannot just look at this table and be like, yeah, we're good. So what you need to do in your calculator, you need to enter January into one list, and July into another. And then we're going to find the list of differences because all our math is going to be based off a list of the differences in temperature. Okay? Luckily, I did all of this earlier, so it won't take me forever to type everything in. So you should have January and July in your calculator if you're going to do this with me. All right. Again, we need to look for the differences. So in list 3, we are going to find the differences in temperature. So if you highlight where it says L3, so you have to actually go above the first cell, so you go to the actual title. You can type in, I'm going to do July minus January, that just seems to make more sense. I'm going to do L2 minus L1, and it's going to subtract all of those pairs for us. All right, so now we have our list of differences. We are only going to be using this list for everything that we do for the rest of the mechanics and everything. I am only worried about the differences in the pairs, right? I could care less about individual temperature in July. All right, so we need to look at a plot of list 3 then. I need to look at the plot of the differences. So I'm going to go to stat plot. I'm going to do a normal probability plot. I keep trying to convince you guys these are the best choice, but it gives you a scatter plot of the data. So make sure, or not scatter plot, sorry, a dot plot of z-scores. So it looks like a scatter plot. All right, so we've got a data list and list 3. Again, I'm worried about the list I have the differences in. And I hit graph. You don't have to hit zoom 9. I can erase this little red thing right there. Okay, so if I'm looking at my normal probability plot, is this line reasonably straight? So I would say that. I would say a normal probability plot of the differences, so we're talking about the differences, is reasonably straight. The data is approximately unimodal or approximately normal or is roughly unimodal and symmetric. That's what that means. So looking at a normal probability plot of the data, it's reasonably straight. So it's either roughly unimodal and symmetric, or you can say that it's approximately normal. So have my conditions been met? Yes. So because the conditions have been met, I can construct a paired t-interval. Okay, so I have, again, we're looking for the mean and the differences, plus or minus a critical value with n minus 1 degrees of freedom times the standard error of those differences. How am I going to find these two numbers? Am I going to find the average difference and the standard deviation of the difference? So you can do that by hand? Well, how are you going to do it? All right, you're going to use your calculator. You're going to do one variable statistics for your difference list, list 3 in my case, and it's going to give it to me. So list 3, I get a mean of the differences of 36.92, and a standard deviation of the differences of 8.66. It said n equals 12. That means there's 12 cities. So what's my degrees of freedom going to be? 11. 12 pairs minus 1 is 11. And so then how am I going to find my critical value? How do I find the critical value for an interval? And what do we put that into? Correct. We use inverse t. We're trying to be 90% confident. So you do 1 minus 90, we have 10% left over. We divide it in half. So we have an area of 0.05 and 11 degrees of freedom. Bailey told me all those things, so we should know those things. All right, you use inverse t in your calculator. So 0.05, 11 degrees of freedom. I get 1.7 something, 1.796. So all of this stuff, so I can fill all of this out. I've got 36.92 plus or minus 1.796 times 8.66 divided by the square root of 12. Right? And I can just do the math. So I have 36.92 minus that. 36.92 plus that. So I have an interval of 32.43 degrees to 41.41 degrees. So now I need to get a conclusion of what that means. So I am 90% confident. Some of you guys are losing it on your latest quizzes and things about what to say with an interval. You're starting to ad-lib. I told you that was a bad idea. You're starting to say like things like 90% of the time and stuff, and that's not necessarily true. All right, so I'm 90% confident. So what are we looking for? The average difference in temperature. And then we probably want to tell them which way we subtracted. So I'm going to put July minus January here in parentheses. Is between 32.43 degrees and 41.41 degrees. So again, in this case, we're looking for average difference in temperature. We're just talking about intervals today. Again, there isn't a paired t-interval in your calculator, but there is a one sample t-interval in your calculator. So if we wanted to check this in our calculator, stat test, we're just going to use a one sample t-interval, which I think, yeah, it's just called t-interval. We have the stats, we also have the data in the calculator, so I'm going to use the data because why not? I'm using list 3 as my list because that's the list of the differences. And I want to be 90% confident. Hopefully this is right. Yeah, 32.427, 32.43, 41.406, 41.41. It gives you the mean and standard deviation of the differences that we already have. So easy way to check the response to make sure you did it correctly. Right? So again, there's not a paired t-interval in your calculator. It's just one sample mechanics based on a list of differences. Okay? Question.